Hello students, welcome to Shri classes. We will continue with lecture number 2, chapter 13, Magnetic Effects of Electric Current. In our last class, we saw the Oster's experiment. A current carrying conductor produces a magnetic field, and that was witnessed by the deflection of the needle of the compass. A current carrying conductor becomes a magnet. It produces magnetic field, and also the compass needle, as it is made up of a magnet, whenever that is brought in the vicinity of the current carrying conductor, between two magnets there exists an either attraction or repulsion force, because of which the deflection of the needle of the compass takes place. And that is a witness for saying that a current carrying conductor produces a magnetic field. In that case, in this lecture we are going to see what are the patterns of the magnetic fields, field lines and their directions in case of a current carrying straight conductor, a current carrying circular loop and a current carrying solenoid. So these are the three parts in which we will be studying the pattern of magnetic fields produced, the direction of the magnetic fields produced, and if the conductor becomes the magnet, which is the north pole and which is the south pole of the conductor. So this is what we are going to study now. Of course, with the straight conductor we are going to study the right hand thumb rule also, that is used to find out the direction of the magnetic field, meaning the direction of the magnetic field lines, because it is a vector quantity. So magnetic field due to a current through a straight conductor, this is something like this. A straight conductor will connect the battery terminals for this conductor, and let us study the pattern of magnetic field or the magnetic field lines produced by a straight conductor. Then we are going to study the current through a circular loop. This is a circular coil for which the battery terminal is connected, the battery is connected. In this case, how this coil behaves like a magnet, what are the pattern of magnetic field lines. Finally, there is a solenoid. We will define what is a solenoid, and in that case, if the current is passed through the solenoid, what is the pattern of magnetic field lines. Important one note here, the pattern of magnetic field around a conductor due to an electric current flowing through it depends on the shape of the conductor, and therefore three peculiar shapes such as a straight conductor, a circular loop or a coil and a solenoid. So these are the three cases in which we will study the pattern of magnetic fields. So first case, magnetic field due to a current through a straight conductor and associated law, that is right hand thumb rule, to find out the direction of the field lines. These two we'll study first. Here there is a straight conductor and a battery terminals are connected here. Whatever the points that I have mentioned in the PPT, let us discuss these points on the board, and then you will be directed to the PPT for making the notes. So let us have a look at the board. I will explain the things on the board now. Now let us study magnetic field due to a current carrying conductor which is a straight conductor. This is a straight conductor. I hope you are able to see clearly the diagram here. A straight conductor is taken. The ends of the conductors are connected to battery terminals. This is the positive terminal, negative terminal. So therefore this end is connected to the positive terminal and this end is connected to the negative terminal. Now here this is a small cardboard through which the conductor has been inserted through. A hole is made at the center and this conductor is inserted through the cardboard. Now if I switch this on, this conductor produces the magnetic field. How do you witness the magnetic field around the conductor? We can witness the magnetic field around the conductor by taking a small compass towards the conductor. whenever a small compass is taken towards the conductor, the needle of the compass will get deflected. Generally, when the compass is not in the vicinity of such any magnetic field, the pointer will direct towards the geographical north and south. But when the compass is taken closer to the conductor, when it is switched on, let me switch it on first here. Let us switch it on. Okay. Now, so under this situation, if the magnetic compass is taken near this conductor, the needle will get deflected, indicating that there is a magnetic field produced around this conductor. How do you confirm this phenomenon, production of the magnetic field? By one more means. What we can do here is, let us switch off this now. Sprinkle iron particles on this, iron filings, sprinkle iron filings on this cardboard, and then switch on. Gently tap this cardboard like this. In that case, the sprinkled iron filings will arrange around the conductor in the form of concentric circles. The iron filings will align themselves along the magnetic field lines. Therefore, the concentric circles around this conductor indicate the magnetic field lines. So, this is how the production of the magnetic field lines take place. I'll draw here three circular, three circles. That means they will get arranged along the circular path. First one, in order to understand, and then comes the second one, and one more, the third one. These are the concentric circles along which the iron filings have got aligned themselves, and this is how the magnetic field is produced around the current carrying straight conductor. Fine. That means there are two ways by which we can confirm the presence of magnetic field produced by the straight conductor that carries electric current. One is by taking the compass needle, which gets deflected, and by sprinkling the iron filings and gently tapping over here, the iron filings will get arranged themselves in the form of concentric circles. Question arises, what is the direction of this magnetic field? One way to identify the direction of these magnetic field lines is, take once again the magnetic compass, place in the vicinity or place on any of these circles or place near this one, near the conductor. What happens? The direction pointed by the north pole of the magnetic compass gives you the direction of these field lines. Because if these are the concentric circles, something like this, if these are the concentric circles, okay, definitely we need to put arrow here, either this way or this way. Either this way or this way, I need to put arrow. That why is that arrow is required? Because that gives the direction of the magnetic field line. So if I take a compass needle over here, say this is a compass needle, generally if it is pointing like this, in the absence of any magnetic field, whenever this is brought near this one, the deflection of the pointer gives you the direction of the magnetic field line. When I say the deflection of the pointer, it is the deflection of the north pole. So the deflection of the north pole of the point of the needle gives you the direction of the magnetic field line. Now you can see here, we can conclude something like this. Suppose if I bring the compass over here, it may show me something like this. It may point towards like this. That means I can definitely say, if this is the pointer, then the direction of the magnetic field lines is like this. If this is the pointer this way, then the direction of the magnetic field is this way. Now if the pointer is directing towards this way, then definitely I can conclude that the magnetic field lines direction is this way. something like this. So can I put the arrow over here like this? Yes, definitely I'll be able to put here, and here also one more opposite side, so that you'll come to know. But there is an alternate way of finding the direction of magnetic field lines. What is that alternate way? And that is called the thumb rule. What is that thumb rule talks about? See, if let us imagine that this is a conductor which is carrying electric current. If we imagine that we are holding a current carrying conductor in our right hand such that the thumb, if the thumb points towards the direction of the current, then the wrapped fingers around the conductor give you the direction of the magnetic field lines. Once again, imagine you cannot hold a current carrying conductor in your hand. Imagine you can see, you have to imagine here, just a moment. You cannot hold a current carrying conductor in your hand. Why? You will be electrocuted, and therefore you have to imagine that you are holding a current carrying conductor in your right hand such that the thumb points towards the direction of the electric current. Here I have marked this arrow which indicates the direction of the electric current in this conductor. So let me hold my hand, right hand, in such a way that the thumb points towards the direction of the electric current. In such case, the fingers wrapped around the conductor give the direction of the magnetic field lines. It is very clear for you. And therefore, let me apply this rule over here. See here, this is a conductor, and here this is the direction of the electric current. Direction of the electric current is from positive terminal to the negative terminal over here. Positive terminal to the negative terminal. Direction of the electric current is upwards, and hence if I hold this conductor, imagine that I am holding this conductor, the thumb is pointed upwards, and therefore the curly fingers will give me, the wrapped fingers around the conductor give me the direction of the magnetic field lines, and hence it is correct now. The direction of the magnetic field lines are this way, like this from the behind, isn't it? And therefore this is the direction of the magnetic field lines which is given here. Now what happens if the direction of the current is reversed? See here, if the direction of the current is reversed, what happens? Let us see here itself. Let us take something like this. That means this right hand should be pointed down, isn't it? So let me hold a little bit different way so that you will understand. Okay, now once again, this is a current carrying conductor. Direction of the current is reversed. It flows from top to bottom now. In this case also, take your right hand and point it towards the direction of the current in the conductor, and once again the curly fingers or the wrapped fingers give you the direction of the magnetic field lines. And therefore here let me explain once again. In this case, here there is a conductor. Suppose this is a conductor here with single line, it is enough. Now this is positive terminal, this is negative terminal. Therefore the current through this conductor from top to bottom, this is the direction of the current over here. In this case, what is the direction of the magnetic field lines over here? It produces the magnetic field line around the conductor in the form of concentric circles. And what is the direction over here? Let us see this now once again. This is what? This is the conductor, and right hand, thumb, and see here, you can see this. The curly fingers indicate the direction of the magnetic field lines, and therefore the direction of the magnetic field lines over here, it is something like this, from here to here, and here it is from here to here. Yeah. Therefore, one way of finding the direction of the magnetic field lines is by means of the magnetic compass. The direction of the pointer of the magnetic compass gives you the direction of magnetic field lines, and the other way to find out the direction of magnetic field lines is by means of the right hand thumb rule. What is that right hand thumb rule? Once again, imagine that we are holding a current carrying conductor in our right hand, such that if the thumb point towards the direction of the electric current, then the wrapped fingers around the conductor give you the direction of magnetic field lines. I hope this you have understood. Couple of properties we'll study now. Now we have understood a battery connected to a conductor. When it is switched on, current passes through, it produces magnetic field lines, and we witnessed the magnetic field lines by means of a magnetic compass, and also we could find out the direction of magnetic field lines either by the pointer of the magnetic compass or by means of the right hand thumb rule. Okay, now couple of points are there. I'll read from my PPT and then explain. Let us see. First point, current through straight conductor produces magnetic field around it, and it can be detected by the deflection of the compass needle. Yes, we explained that. For example, here if I keep a compass over here, it will deflect. That is the first point. Second point, magnetic field lines are in the form of concentric circles. Yes, magnetic field lines around the straight conductor are in the form of concentric circles, the direction of which can be given by either a compass or a right hand thumb rule. Yes, both we studied. Now, what is the magnitude of the magnetic field? What I am talking here is the magnitude of magnetic field. It is writing very lightly. Magnitude of what do you think is magnitude depends upon the magnitude. I'll read a couple of points here. The magnitude of the magnetic field produced at a given point, at any point, increases as the current through the wire increases. If I increase the current through this conductor, the magnetic field strength also increases. It is directly proportional to the magnitude of the electric current. For a given current in the conductor, the magnetic field produced decreases as the distance from the conductor increases. Simple. The magnetic field strength is high near the conductor. As we move away from the conductor, the magnetic field strength decreases, and this is the next point. So these are the properties, with a couple of properties of magnetic field lines around the current carrying straight conductor. Now, this cardboard has been inserted at this distance, at this point from here, maybe at some distance, at approximately middle over here. What do you expect? Do you think that the magnetic field is present in the conductor only at this point? No. The magnetic field is present from this end to this end. That means the envelope of this, or these circles, basically these circles are the what we call these concentric circles, magnetic field circles, will produce an envelope of magnetic field lines around the straight conductor. So you can imagine the magnetic field around a straight conductor something like this. If this is a straight conductor, okay, if it is connected to a battery terminal, then the entire, this is how the magnetic fields concentric circles will be there. So it will be in the form of a cylindrical shape. The magnetic field around a straight conductor is in the form of an envelope of a cylinder. You understood? So everywhere you can find the magnetic field, but in order to understand, we took the cardboard, inserted at one particular point, sprinkled the iron filings, and understood and studied the pattern of the magnetic field lines which are in the form of concentric circles. What else is to be discussed? Let me check through the PPT and then we'll further discuss. Yeah, direction of magnetic field lines due to a current carrying straight conductor, right hand thumb rule. Let us see. Imagine that you are holding a current carrying conductor in your right hand such that the thumb point towards the direction of the current. In that case, the fingers that wrap around the conductor give the direction of the magnetic field lines around the conductor. So this is what we have studied. Now, there is one more rule which is called Maxwell's Corkscrew rule. What is this Maxwell's Corkscrew rule is? See, in all these wine bottles and all, we have a cork. Cork is something like, it is used as a lid for closing the top of the bottle. Something like this, it's top of the bottle. Of course, the corks are used for even in laboratories we use, isn't it? At the neck of the round bottom flask, etc. The corks are used for inserting the thermometers and all. So there is a Maxwell's screw rule. What it talks about is, suppose this is a screw here. This screw will have something like this. This is a screw over here. Okay. What is this Maxwell's screw rule talks about? If this screw is driven inside the cork, if it is driven inside the cork, then the direction of rotation gives you the direction of field lines. That means if the screw is driven inside in the direction of the current, then the direction of rotation of the screw gives the direction of magnetic field lines. Meaning, suppose in this case, this particular case we'll consider current is flowing downwards. That means the screw is driven towards the bottom. So if it is to be driven at the bottom, then definitely this is to be rotated this way. The screw is to be rotated this way. Meaning the direction of rotation is like this. Check here. Here I have marked this with blue. This is the conductor and the blue one indicate that this is how. Right hand thumb rule, exactly something like this. So same thing here. If the direction of the driving the screw is in the direction of the electric current, then the direction of rotation of the screw gives you the direction of magnetic field lines, and that is called Maxwell's corkscrew rule. Of course, that is many times we use it. What else? Yeah, these are the things. I think I have discussed everything with respect to magnetic field produced in a current carrying straight conductor. Magnetic field produced in a current carrying straight conductor. Anything is left here? Yeah, I think I have done it. Now there is one small example numerical is there. Let us see that. A current through a horizontal power line flows in east to west direction. What is the direction of magnetic field at a point directly below it and a point directly above it? So solution I will read first and then we can analyze. The current is in the east-west direction. Applying the right hand thumb rule, we get that the magnetic field at any point below or above the wire turns clockwise in a plane perpendicular to the wire when viewed from the east end and anti-clockwise when viewed from the west end. Did you understand it? No. Let us draw the diagram here first. Let me clear the board to some extent. There is a conductor, a power line. So this is what the power line looks like. This is a power line. Direction, if I need to fix up, let me fix the direction. North, south, east, west. Is it clear for you? Right side east always, east, west. Now, thing is, the current is in the east-west direction. It is east-west direction. This is east here and this is west here. The direction of the current is in this direction, from east to west. This is the direction of the current. Question is, here, what is the direction of the magnetic field at a point directly below and at a point directly above it? See here, if this is a conductor, then how do you identify the direction here? The right hand thumb rule. Say for example, this is how I can use once again a conductor with the direction of current in this side. Use the right hand thumb rule. I am using the right hand thumb rule in such a way that, imagine that we are holding that, what is that wire called? It is the power line. This is the power line. I am imagining that I am holding the power line over here with my thumb pointing towards the direction of the current. In that case, the curly fingers will give me the direction of the magnetic field lines. So from the top, if you see like this is how the magnetic field lines are moving. Above, the magnetic field lines are entering into the board, and below, the magnetic field lines are coming out of the board. And therefore, in a plane perpendicular to this one, like this, if I take a cross section over here, above, magnetic field line is entering inside and below it is coming out of the board. So what is the solution given here? So this is how, first of all, I can something like this, or better to draw this way. Yeah, this is upwards here, and this is how the direction can be given. It is going that side and coming out. So at the bottom it is coming out, on the top it is going inside. What is the answer? The current is in the east-west direction. Applying the right hand thumb rule, we get that the magnetic field at any point below or above the wire turns clockwise in a plane perpendicular to the wire. Suppose this is wire here, and in a plane perpendicular to wire is this plane. This is a plane in a perpendicular to this wire. Let me look from the east side like this. In this case, this is a clockwise. If I look from the east side, this is a plane which is perpendicular like this, exactly. See here, exactly like this. I am looking from the east end. This is the power line. Current is flowing that way. Clear? Now it is, current is going through this. I am looking at this plane. If I look from the east end, this is like this. Behind it is coming. Therefore, I will say this is a clockwise. What is that is written? Turns clockwise in a plane perpendicular to the wire. The current in the east-west direction, applying the right hand thumb rule, we get that the magnetic field turns clockwise in a plane perpendicular to the wire when viewed from east end. Yes, from I view from the east end, it is clockwise. Now, let me come to the west end. Just a moment, I am entangled by the wire here. Okay, now that's okay. I hope that's okay, no problem. Now, I am viewing it from west end, this side. How is the magnetic field line? Like this. It is going and coming like this. So, from the west end, it is anti-clockwise. I hope you are able to understand. So, this is a power line. When the current flows from east to west direction, above and below, if I need to find out the direction of the magnetic field, then let me view from the east side. In that case, the direction of the magnetic field line is something like this. This is clockwise, and when I view from the west end, the magnetic field direction is anti-clockwise. That is what the answer given. See, physics, all this requires to some extent the imagination, and yourself, if you read all these questions and try to imagine, it would be better. Yourself, you need to realize it. Okay. Fine, with respect to straight conductor, let me direct you to the PPT now, make a notes, and then we'll go to the circular loop. Yeah, here magnetic field due to a current through a straight conductor. Draw the diagrams, make all these notes, pause the video and make the notes. Similarly, the right hand thumb rule, here it is given. Draw the diagram, note down. Also the Maxwell's corkscrew rule. This Maxwell's corkscrew rule, it is given at the bottom of the page in your textbook chapter. Please find out that one. A small note is given, that is enough to understand. I'll read once again here. If we consider ourselves driving a corkscrew in the direction of the current, then the direction of rotation of the corkscrew is the direction of the magnetic field. And the example which I discussed, 13.1, that is a current through a horizontal power line. Such questions can be expected in the exam. Okay, next is, let's see. Yeah, magnetic field due to a current through a circular loop here. There is a difference between a loop and a coil. A loop is a single strand of wire and a coil is multi strands of wire. Or a single loop or a loop is a single wire and a coil is the collection of such wires. A coil is a collection of n such turns. This is called one turn, and a coil is collection of n number of such turns. If the current passing through this one turn is 1 ampere, and if there are such 10 number of turns here, the total current that passes through this is 10 amps. I hope you are understanding and the difference between the loop and the coil. Next, okay, there are a couple of things over here. First, let me try to explain this on the board. That is one single loop, and then we'll get back to the PPT for making the notes. Now we'll study magnetic field due to a current carrying loop and coil. As I said, loop contains only single turn and coil contains many such turns, n turns you can say. This is the pictorial representation of a loop, which is a single coil, and these are the end terminals of the loop, and these two end terminals are connected to the battery terminals. This end is connected to the positive terminal and this end is connected to the negative terminal, and therefore the direction of the current is like this. This is the direction of the current. So let us switch on, sprinkle some iron filings on both the, first let us sprinkle the iron filings, assume that you are sprinkling the iron filings, and switch on and check the magnetic field patterns or the magnetic field line patterns. We'll see that first. So let us switch on. The dot indicates switching on. A current is passing through this one. Now here, in order to study the magnetic field line patterns at this point and in this point of this coil, let me apply the right hand thumb rule and identify the direction of the magnetic field lines and their pattern. First of all, with respect to pattern, at this point, if I sprinkle iron filings and gently tap over here, I observe that the field lines are concentric circles around this coil. Around this coil at this point, the field lines are in the form of concentric circles. So let me draw the concentric circles. Two lines I'll represent over here, but there are many magnetic field lines. For our understanding the direction, I am considering only two field lines. One is this way and another is this way. Okay. Yeah. This is here also we observe the field lines are in the form of concentric circles. the field lines are in the form of concentric circles. How did you identify this? This is a current carrying conductor in a loop. Sprinkle some iron filings, switch on, gently tap the board. This is a cardboard. You find that the iron filings align themselves in the form of concentric circles, and therefore we can conclude that the magnetic field lines around this coil at this point are in the form of concentric circles. Second thing, how do you confirm the presence of magnetic field? If I take a compass needle and bring in the vicinity of this coil over here, the needle of the compass will get deflected, which again witnesses the magnetic field produced by a current carrying loop here. Now, what is the direction of the magnetic field lines at this point and at this point? Apply the right hand thumb rule. As I said, here I am considering, this is how it is. This is the conductor. Imagine that you are holding this coil. Imagine that we are holding this coil in our right hand, something like this, right hand, with the thumb pointing the direction of the electric current. In that case, the curly fingers will give the direction of magnetic field lines like this over here. That means the field lines are entering into this loop. If you look at this, this is the space inside the loop. See here, I can say the field lines due to this coil at this point are entering into the board, like this. They are entering, and therefore the direction can be like this. Here, this is the direction. What about this side? I require that one. Yeah. Now, at this point, let us try to find out the direction of the field lines. See here, this is okay. I have not marked here the direction. Here, this is the current direction. Here, this is the direction of the current here, and in this way, the current goes through this and comes back. Therefore, this is the direction of the current. I hope it is clear for you. This is the direction of the current here, I, and this is the direction of the current here. Now, the current is going through this and coming back like this. So, see, this is how. Yeah, here this is the conductor. Now I have to hold this conductor in my right hand like this, correct? So what I'll do here is, see, this is how it is and coming like this. Is it clear? So I can hold like this also, like this. This is the arrow downwards at this point, and hold this in the right hand. This is the direction. That means the field lines at this point are also entering into the board in this side, entering into the board, and those are coming out of the board on this side, entering here, coming out this side, and therefore the direction can be represented as, here the direction can be represented as like this: inside, outside, inside, outside. So if you look at the magnetic field lines direction, this is how it is, the direction. Yeah, something like this. Dear students, I hope you are able to understand here. Magnetic field lines at this point, by applying the right hand thumb rule, those are entering into the board. While applying the magnetic field, the right hand thumb rule for this side of the conductor, the field lines are entering inside and those are coming like this. So the field lines are entering inside the space enclosed by this loop. Within the space enclosed by this loop, the field lines are entering into this one, or can I say the field lines are merging into this one? Merging means or entering into this one. Okay, and therefore this is the pattern. Let us study a couple of points over here. The direction of the magnetic field lines at the center is almost uniform. Why it is uniform? If you look at the spacings between these magnetic field lines, it is almost parallel at the center, but when we come towards the conductor, those are in the form of concentric circles. Parallel lines represent uniform magnetic field. All these parallel lines are in the same direction. So within the space enclosed by the loop, the direction of the magnetic field lines is same. You got it? And at the center of the loop, the magnetic field lines being parallel almost, it is a uniform magnetic field. From here or from here, if I move away from the conductor, the magnetic field strength decreases. The lines are crowded near these 2 points. As we move away from the conductor, the density of the magnetic field lines decreases, and therefore the field strength weakens. One important point here is this particular loop, it is acting like a magnet here. So generally a magnet has 2 poles. One is a north pole and one is a south pole. How do you identify which is a north pole here and which is a south pole? That means this is a coil over here. If this is a coil, I can consider this coil to be something like a coin. I don't have now something like this. Any coin is available? Yeah, something. It's a very small coin is available. Something like this coil. If I consider this, it has got 2 faces. One is the front face and one is the back face. I hope you are able to see. One is the front face, one is the back face. So this coil can be visualized to be consisting of 2 faces. Which we are seeing is the front face, and in order to see the back face, I have to go behind this board. Okay, now fine. As this coil becomes a magnet, we need to identify the polarity of this loop, which is the south pole and which is the north pole of this loop. So if loop is considered to be in a plane, then in order to identify the south pole and north pole, we should know about something called the clock rule. So what is that clock rule basically? This is called clock rule, C-L-O-C-K, clock rule. What is this clock rule talks about? If we are facing the coil, plus minus, current is flowing this way. Okay, if I am facing the coil and if the current moves in the clockwise direction, if the current flows in the clockwise direction, then whether it is a south pole or a north pole, how to identify? See here. Here this is S here, S is written, the ends are marked with arrows. Now the direction of the current and the direction of this S is matching. If I write this as a S, that means the face that we are looking is south pole, and therefore if the current flows in the clockwise direction, then the face which we are looking at, that face behaves like the south pole. Next, here the current flows this way. Okay, now it is anti-clockwise. In order to find out this anti-clockwise, Check now. N is written, which indicates a north pole. If we are facing a coil and if the current flows through the coil in anti-clockwise direction, the face of that coil behaves like a north pole. This is called the clock rule. Once again I will explain. The face that we are looking at, in that face, this is a coil here and we are looking the front face of the coil. If the current flows in the clockwise direction, the face of the coil behaves like the south pole, and if the current flows in the anti-clockwise direction, and then it behaves like a north pole. This is one way of recognition. Therefore, here if I am facing this coil, the current is flowing from here to here. The current is flowing from here to here. That means the current is flowing in a clockwise direction if I view from the south, from the front, and therefore this is the south pole. The front face of this is a south pole. What about the back side face? If I stand behind and observe this, the current is flowing like this. If I observe from the back side, the current is flowing in anti-clockwise direction, and therefore the back face of this coil or the loop, basically loop and coil interchangeable, okay? So if I see from the back side face, I observe that the current is flowing in anti-clockwise direction, and therefore that behaves like a north pole. So the front face is a south pole and the back face is a north pole. This is identifying the direction, this is identifying the polarity of a particular loop which behaves like a magnet. A little bit information I'll write over here. This is south pole for clockwise direction of current, and this is anti-clockwise direction, north pole if current flows in anti-clockwise direction. Okay, north pole for anti-clockwise. So you are able to remember the clock rules now? Okay, now without a clock rule, how would you be able to remember the south pole and north pole? Already we have studied that in a magnet, if this is the north pole and this is the south pole, these are the magnetic field lines. They emerge from the north and merge into the south. They emerge from the north and merge into the south. Correct? This is what we studied in this thing. So if there is to be a north pole, the field line should emerge out. If this is to be a south pole, if you are facing from that side, this is if it is to be a south pole, the field lines are merging into this one, and therefore if I look at this coil, when I face over here, within the space enclosed by the coil, the direction of the field lines are entering into the coil, merging into the coil, and therefore this face of the coil acts as the south pole, because those are merging into the field lines are merging into the face, and the face is called the south pole. Now when I go back behind this, when the field lines are entering over here, from the back side if I see, the field lines are coming out of the board. Those field lines are coming out of the board if I see from behind. So the field lines emerge out, and therefore the back side of this loop, the back side face acts as a north pole. I hope you are able to understand. And therefore, a current carrying circular loop behaves like a magnet. The front face will act like a south pole if the direction of the current is in clockwise. In that case, the back face of the loop acts as a north pole. If I change the direction of the current over here, then the front face will become the north pole and the back face will become the south pole. I hope you have understood very clearly how to identify the faces of the loop which act like south pole and north pole. If one face acts like a south pole, the other must act like a north pole. Okay? What else is there? Let me read certain points over here and confirm. Current through a circular loop. A circular loop refers to a single turn. A current carrying circular loop behaves like a magnet, and north and south poles can be identified. Yes, we discussed. In the vicinity of the wire, field lines are nearly circular. As I said, closer to the loop over here, closer to the conductor, in the vicinity of the wire, the field lines are almost concentric circles, and field lines are nearly circular. Within the space enclosed by the loop, magnetic field lines are in the same direction. Inside this loop, the space, the direction of the field lines is in only one direction. All the field lines are entering according to this diagram now. Near the center of the loop, the field lines are nearly parallel and can be assumed to be uniform. Also, field lines are perpendicular to the plane of the loop. If this is the plane of the loop, field lines are going like this. If this is a loop over here, field lines are going like this. That means plane of the loop and the field lines entry both are perpendicular. If this is the plane of the loop, the field lines are entering like this. Polarity depends upon the direction of the current. As I said, if you view from the front, clockwise direction makes the face of the coil south pole, anti-clockwise direction makes the north pole. Identifying polarity, looking at the face of the loop, if the current flows in clockwise direction, then the face has south polarity, and if the looking at the face of the loop, if the current flows in anti-clockwise direction, the face has a north pole. This is what we have studied. Next, let me see what else is I have discussed in the PPT. Coming to current through a circular coil. Coil means it is n number of turns. N means say 100 turns, 20 turns, 1000 turns, etc. That means more than one turn is considered to be a coil instead of a loop. So, current through a circular coil of n turns, whatever that we discussed so far, all that is applicable to a coil also. Absolutely, there is no difference between that. Only thing is, in order to you may ask a question, why should we go for the coil here? Suppose if this acts like a magnet and if it has some application in practical fields, question arises how to increase the strength of the magnetic field in a loop. Say for example, magnitude of the current, say for example here I have only one loop, and if I want to increase the field strength, there are 2-3 options for me. One is increase the current through this one, but to a large extent if you increase the current, it may become hot and all, and it may not be suitable. And therefore what I will do here is, instead of one number of turn, I will club together 25 turns. I can have about 20 turns, 25 turns, 100 turns, etc. If 1 amp current flows through one loop, then in n turns, n times the current. And therefore, if the magnitude of the current increases, the strength of the also increases. The magnetic field strength of the loop also increases. So let me read here. Current through a circular loop. How to increase the magnetic field strength? Field strength increases if the current in the loop increases. Yes. Field strength can be increased by increasing the number of turns of the loop to form a coil. So if you increase the number of turns, then also field strength increases. If there is a circular coil having n turns, the field produced in n times as large as the field produced by a single turn. That I have explained. This is because the current in each circular turn has the same direction, and the field due to each turn adds up. That is what the explanation is. So I think we have studied all these properties of the magnetic field lines due to a current carrying circular loop. Now I will direct you to the PPT for making the notes. So current through a circular loop, which is a single turn. This is the diagram. You need to note down the diagram also, and this is a clock rule which I have explained. All these points are important. You need to make a proper notes. Pause the video and you can make the note, and camera can be focused to the camera can be focused to have a closer view of the PPT. Next is, you can pause the video to note down current through circular coil N. Why we need to increase, why we can go for coil of N turns is, if we want to increase the magnetic field strength, either increase the magnitude of the current or increase the number of turns in the coil, because the direction of current in each turn is in the same direction, and therefore magnetic field produced in each turn will get added up. By increasing the number of turns, we can increase the magnetic field strength. Okay, so pause the video and make a note of this. Next is magnetic field due to a current in a solenoid, which is important. Of course, all these are important. Let's see what is that one. Here, current through a solenoid. This is how the solenoid looks like. There is one insulated cylinder, and over which an insulated copper wire is wound in the form of a cylindrical shape. See here, this is an insulated pipe or something like that, on which you can wind the insulated copper wire. This assembly forms a solenoid. Let us study the definition of the solenoid here. A coil of many circular turns of insulated copper wire wrapped closely in the shape of a cylinder such that its length is greater than its diameter is called a solenoid. Here, an insulated copper wire wound in the shape of a cylinder whose length is greater than the diameter is called a solenoid. Suppose the diameter is greater than the length, then it becomes a coil, and hence the length of this solenoid or the length of the cylinder should be greater than the diameter of the cylinder. In that case, such an assembly is termed as a solenoid. The definition is very important. What is a solenoid? An insulated copper wire wound in the form of a cylindrical shape whose length is greater than its diameter is called a solenoid. Whenever an electric current flows through a solenoid, it behaves like a bar magnet. See here, it behaves like a bar magnet, and the magnetic field lines are produced over here. This is how it is. Okay, one end of the solenoid behaves as the north pole, while the other end acts as a south pole. That means if this is a solenoid, one end, this side and this side, if you look at, one end behaves like a north pole and another end behaves like a south pole. Inside the solenoid, the magnetic field lines are parallel and straight. Inside, these are almost parallel and straight, and therefore inside the solenoid the magnetic field strength is uniform, whereas outside you can see there exists a scattered distance, and therefore when we move away from this solenoid the field strength decreases, whereas inside the solenoid the magnetic field strength is uniform because the magnetic field lines are almost parallel. Okay, this is something about the solenoid. I would like to discuss the same on the board, which is very, very important there, and how to identify the polarity and all. Identification of the polarity in the solenoid is only by means of a clock rule. Otherwise it is very difficult to understand, and hence you have to learn the clock rule. Let me check what else is written here. Yeah, factors on which magnetic field depends in the solenoid, that also we'll discuss, and then the same description a bit in detail I'll explain on the board. Let us read this. Factors on which magnetic field depends. Field strength can be increased by increasing the current through the solenoid. Magnitude of the current, if we increase, the field strength also can be increased. Field strength can also be increased by increasing the number of turns per unit length. Here if I count 1, 2, 3, if this is 1 centimeter, then in 1 centimeter I have 3 turns. If I increase the number of turns in 1 centimeter, in that case the strength also can be increased. So the field strength can be increased by increasing the number of turns per unit length of the solenoid. Field strength can also be increased by keeping a soft iron core inside the solenoid along the axis. This is a soft iron core, inside it is placed. In this case, the magnetic field strength of this entire assembly can be increased. Okay. Identification of the polarity I'll discuss on the board. Electromagnet. Such an assembly is called electromagnet because as long as the current flows through the solenoid, this entire assembly behaves like a magnet. When the current is switched off, this will no more retain its magnetic property. So it is called an electromagnet because as long as the current flows, it behaves like a magnet. When current is switched off, it will get demagnetized. Okay. These aspects, along with identification of polarity, I would like to explain on the board, and then once again I'll direct it to the PPT for making the notes. This is a typical solenoid. See, how do you define this solenoid? An insulated copper wire wound in the shape of a cylinder whose length is greater than its diameter is called a solenoid. The length should be greater than the diameter of this one. Otherwise, if the diameter is greater than the length, then it will become a coil. Hence, in the definition of a solenoid, we say that this is a copper wire wrapped around in the form of a cylindrical shape whose length is greater than the diameter is called a solenoid. Now, here this solenoid is connected to the positive terminal and negative terminal of the battery, and it is switched on. So this will behave like a bar magnet. What do you expect if it has to become like a bar magnet? Then definitely it will produce in all three-dimensional region the magnetic field lines, isn't it? So the field lines will be something like this. The field lines will be remember, the field lines are closed continuous loops. Let me have one more. Yeah, and this side also. And one more. Yeah, this is how the field lines look like. Now, here the question arises. Anyway, before the question, a current carrying solenoid behaves like a bar magnet, and the field line patterns, the magnetic field lines patterns are almost similar to the bar magnet. And how to identify now the direction of the magnetic field lines? Before that, the field lines within the solenoid, inside the solenoid means inside this assembly are almost parallel to each other, meaning the field strength is uniform inside the solenoid. Externally, if we move away from the solenoid, the field strength decreases. That is one characteristic which you must know. How to identify if this behaves like a magnet? How to identify which face of the solenoid is a south pole and a north pole? There are two faces over here. This side face, the circular face, is called A here. Let me call this A, and this side it is B. Let me write somewhere here. This is A here and this is B. Now, how to identify which is a south pole and which is a north pole? That is the question. I'll make use of the clock rule. What is the clock rule? If I are facing a coil or a loop, if the direction of the current is clockwise, it is the south pole. If the direction of the current is anti-clockwise, it is a north pole. Look here, the direction of the current is going like this. Behind it is going, once again it is coming from the back side and going like this. Therefore, if I look this face A from this side, it is something like this. The current is anti-clockwise direction, and therefore here I'll write, if I'm facing this way, or this arrow is misleading, what I'll do here is, if I check this side, the current is flowing this way, anti-clockwise, and therefore this is a north pole. This is a north pole. Therefore A acts as a north pole. And what about the other this side? If I come this side and look at this face, the current is moving like this and it is going behind. So the current moves and goes behind the coil and comes out, and therefore this is a clockwise here. In this case, this is a clockwise here, and therefore if this is a clockwise, this is a south pole. South pole. And hence let me mark this with red. Face A acts like a north pole and face B acts like a south pole. What about the field lines now? Direction of the field lines. From north they emerge, into south they merge, and therefore this is the direction. This is the direction of field lines here also. From north pole they emerge and they merge into the south pole. This is the direction. So another two lines now I'll indicate something like this. Therefore this is a north pole, and another two lines here, they merge into this. This is the south pole. So important thing here is identification of the north and south pole is based upon the clock rules. If I look from this side, the direction of the current is anti-clockwise, and hence it is a north pole. Face A of the solenoid acts like the north pole, and if I look from this side of the solenoid, current is going from the front and it is going from the back and it is coming out. So this is a clockwise here, and therefore face B of the cylinder acts as the south pole. This is how we should be able to identify the polarities of the solenoid. What are the applications of the solenoid? See, this is called an electromagnet. Actually, the solenoid is nothing but an electromagnet. Meaning, as long as there is a flow of electric current, it behaves like a magnet. Once the electric current is switched off, this assembly will get demagnetized and you do not observe any magnetic properties. And therefore, this is called electromagnet. How do you increase the strength? The number of turns per unit length. If I increase the number of turns per unit length, meaning in the earlier case, if there are 10 turns in per 1 centimeter, I can make it 20 turns per centimeter. In that case also, the field strength can be increased, or by increasing the magnitude of the electric current, we can increase. Or one more way of increasing the magnetic field strength is by inserting a soft iron core inside the solenoid, because the permeability, ability to get magnetized for the iron is very high, and therefore by placing the permeability materials having high permeability, if we place inside, then definitely the magnetic strength of the entire assembly can be increased. So three ways by which we can increase the magnetic strength of the solenoid. Those three ways are: increase the number of turns per unit length, increase the magnitude of the current, or by inserting a soft iron core inside the solenoid. And what are the applications of the solenoid? Solenoids are electromagnets and hence can be used in actuators, valves, etc., where opening and closing of the valves can be done automatically, which will be controlled by the control circuits, that is by electronics we can control. And these solenoids have wide applications in the form of actuators also. For example, if there is a defective item, in order to push that item, we can make use of the electromagnet. There is a wide applications, industrial applications, and I mean, you can remember as these are used as actuators in walls and in walls and all we can use, or industrial applications you can say. This is all about the solenoid and identification of the polarities. What else is to be discussed? That's all. I think we have studied today the magnetic field lines and their patterns through a straight conductor, a current carrying straight conductor, a current carrying loop, a current carrying coil, and a current carrying solenoid. Now I will direct you to the PPT once again for making the notes. Yeah, for a magnetic field due to a current in a solenoid, the definition of the solenoid, the diagram, and the magnetic field patterns, the magnetic field lines and the polarity you can directly copy from the board where I have drawn the diagram, which gives all the details, the magnetic field lines, patterns, which is the north pole, south pole. You can take the notes from the board. Okay, and these things you try to make a note, small note. Factors on which the magnetic field depends upon, and how to increase the magnetic field strength we discussed. Identification of the polarities by means of clock rule, and electromagnet. It can be, it acts like an electromagnet, and there are wide industrial applications. One small note here, for identification of the polarity we can make use of thumb rule, but you know it is very difficult for you people to get confused with the thumb rule which we use in case of the solenoid. It is a reverse process, hence I am not discussing. If your teachers have discussed, it is fine. I am not going to discuss identification of the polarity of the solenoid by means of thumb rule. Thumb rule will restrict it to the identify the magnetic direction of the magnetic field lines in a straight conductor. Okay, so make a note of all this one. Okay, now I think camera can be adjusted to cover me also. We are going to end the lecture now. This is the end of the lecture number 2, and we'll stop over here. In my next class, I'll be taking, whenever a current carrying conductor is placed in a magnetic field, it experiences a force, and that is the principle of a DC motor. So we'll see you in the next lecture. Thank you very much for watching.